Okay, so let's here with this Jacob's position. So so it says so what's important that falls from this decomposition that L2 space can be seen as the simply mixing part and the part that corresponds to eigenvectors of the corresponding coupon operators. Coupons F composed with T. And so here, maybe before we discuss the proof, okay, that's going to be good. So here we know that. So we proved that this space, so orthogonal, the space of compact functions, of periodic functions, is orthogonal to this, and we know that the orthogonal component of eigen functions is here. So therefore, this implies this implies this and this. And now if we use this two, then from here, this is the only position. So what's this? If we do this and this here, then we see that the space of the eigenvectors is precisely the orthogonal complement of this space. The orthogonal complement of the eigenvectors. So we combine, then we can use that these two guys are if the space of periodic functions in this context are precisely the eigenvectors of the group. So that's the question what we have here. And now we can use this to complete the proof of Host-Ziegler for k equal to in the bilinear case in the context of ergodic and non-reserved system. So if we let's assume that T is ergodic, and so we want to show that this can exist in L2. Right? Therefore, this is what we do from the first part. We know that if at least one function is weakly mixing, then this limit exists and is equal to 0 to norm. This is what we proved as a consequence of van der Korkut lemma. And now we can use Jacob's Liebsberg decomposition, and we can assume that function f, let's say, is an eigen vector for the coupon operator. So if we define this operator with its second function, which is and we can keep on past here, then we see that this is so the coupon operator, this is the operator, this unitary operator, which is T. And so you see that by the definition, this is equal to this. But in the second function is so this is linear operator, the second function is fixed. So now we see that this F1 is an eigen function for T, it corresponds to eigenvalue lambda. Then it has this form. Okay, so we have this form there. And this what we have here. This also defines unitary operator. Okay. And what's important by the ergodic theorem, the limit for this guy exists in L2. So by von Neumann theorem. And what's important, consequently, we obtain that the limit for this exists in O2 for every function which is in the closure of the eigenvectors of the component operator. So in other words, in this, so for every F1, so let's find this, we have the limit exists. So therefore, but this set is dense in the closure of this space. So therefore, we obtain that this convergence in fact holds for all functions from Ex. And so this implies in particular that the norm of this convergence is uniformly bounded by an infinity of L2 of F2. And this proves, in fact, Hofstra-Ziegler for this function because for whenever F is equally mixing, then we know that this one converges to zero. So that's how we get the Hofstra-Ziegler. So in other words, we know that this so therefore here we obtain the convergence two for this binomial operator. And as I said last time, this if we want to extend this result to the genuinely multilinear operators, 3 linear or more, then one has to do it's much harder. One has to do much more work, and this was done by Post and Kraft, who used the ideas of the hours from the higher order Fourier analysis, and they adapted, his technology to the ergodic setting. That was one important thing. The other thing, they understood, the corresponding characteristic factors with this average. These characteristic factors, they determine the limit of this. So that was a very deep work at the beginning of 2000, and which influenced a lot of things, that afterwards happening and got it here. And independently, it was discovered by Ziegler. And so this theory of characteristic factors they correspond to, they're closely related with some concept of neo manifolds and the sequences and distribution theory on manifolds. It's a very deep theory, but luckily for the purpose of this lecture, we don't need to use any knowledge about characteristic factors. Even the simplest characteristic factor of this space. This space here, this is a billion group, and it's sometimes this space is called chronic factor. So this is the simplest simplest possible non-trivial factor. The other are more complicated and some knowledge from the okay, so that's how we get Hofstra-Ziegler. And now there's a question how this can be used, to derive Roth theorem. And first, this is what we do. We can obtain the following result for compact systems. In function. So here we see, because you see that so far we know that here the limit exists. If we knew that this limit exists and is a product of integrals, then immediately this can be applied, to the deduce Roth. But here, this is not necessarily true. So therefore, we do some work, and so this work can be done by understanding, the following sets whenever whenever f is almost a periodic function. And so this is what we do here. So the proposition is the following. So we have a measure preserving system, almost periodic function, and for every epsilon, there exists J, such that this set, the rest here is synthetic. So which means I, intentionally avoided to introduce this name synthetic path. So syntheticity means that it has non-empty intersection with every interval of length here in this case, J plus 1. Okay, and this holds for this J exists for every epsilon. It's a certain integer. We usually think that this is large integer, and it has this property that this set has non-empty intersection. Normally, you will see how this property that this set has non-empty intersection with every interval like J plus 1 can be used to deduce Roth theorem. So the proof is so let's take a look at the proof of this result. So so we can assume that our function has infinity has not at most 1, and this says its closure is compact, it's pre-compact. So therefore, we can find J such that this set can be covered by a finite number of balls, each centered at this point, and each has radius epsilon over 4. And so this is an open ball. And therefore, we define the following set of those integers such that the distance between those two is smaller than epsilon over 4. And now from this, we can see that this set has non-empty intersection for any integer. And moreover, so therefore, for every S, by telescoping, we can see that this is smaller than epsilon over 2. So here we use the telescoping and the fact that the underlying measure mu is t invariant. So therefore we have also this. And now if we use these two properties, this here, and we use Cauchy-Schwarz, then we can deduce what we want. Because so we start with this average, and we need to show that it has this bound. So this is what we do. We add and subtract. We have to, in other words, remove this dependence on t here from this function to end up with this. So this is what we do. We add and subtract. We replace this guy with f here. So we add and subtract f to this expression. So therefore, it splits into two integrals. And we know that the L2 norm of this is small, smaller than epsilon over 2. So therefore, we use Cauchy. We use Cauchy-Schwarz and the fact that functions f are in L infinity and this bound. So to obtain this. Okay, so therefore we have this lower bound, and this is what we do next. We replace this with f. So the same argument and L infinity bound Cauchy-Schwarz, and we control this by another epsilon. So therefore we end up with epsilon here, and this third power of L3 norm of f. Okay, and so therefore, and this holds for every set, for every integer n in this set, whenever we have this. So therefore, you see that we this completes the proof, because now this shows that in particular this set that satisfies this, it has this property that it has non-empty intersection with every interval of length J plus 1, because this set, the way how we constructed this set here, discovery, it shows that. So S, in other words, S, this set S, is contained in this set. This is what we have shown already. And this set has intersections. So that's how we get this proposition, and this will be very important proposition in the proof of Roth.
So this applies to arbitrarily many factors, not just for two, right?
Yes.
I mean, for the
yes, this works for arbitrary math, but they just adjusted this because we were okay. But yes, for as well as this, this also works. I mean, so here, if we go back here, this theorem you remember for this also works for arbitrary many factors. If we assume that at least one function is with mixing, then this is for arbitrary value true. But I formulated this because we were with wrong. So okay, so let's go back to this. So you see that here today we skip a lot of things, technical things, but this for by purpose, because we want to avoid. I just want to explain this general idea that when you prove something for some class of measure preserving systems, then we have to see what happened. If we ask about especially non-convergence or this kind of problems, we have to understand what happened on the orthogonal complements. Therefore, all these things are purely Hilbert space methods. And now here we have some a nice result from measure theory, which is called this integration of measures. We know many results of this form. It says that so this is particularly important from the point of view of this applications in combinatorics, that many results can be, thanks to this theorem, can be proved only in the ergodic setting, under the assumption that the underlying measure preserving system in question is ergodic, because of this composition. So it says that if we have a probability space in measure preserving map, then there exists probability space, another probability space, and the measure map. In fact, this measure can be injected here with the property that for almost every point in this new space, this new measure is T invariant ergodic probability measure, and so the following this integration of coordinates. So this is some kind of we can think that this is some kind of extremal problem that that any other measure any measure in measure preserving systems can be seen as a convex combination of extremal points which are ergodic measures. So we can think that ergodic measures are because extremal points. So this is generalization of some results from functional analysis in this nice measure theory context. So we skip the proof. This is not very difficult. It requires some knowledge from martingales and conditional expectation to obtain this. So we can think that here this is certain conditional expectation. So in fact, this is some sort of random Nikodym derivative. We can think this way, if you like. Yeah, but let's assume this is a black box. For instance, the nice exposition of this is times word. And let's try to see, how this can be used to provide a ergodic proof of Roth theorem, which is, this result. So we want to understand this limiting behavior of this. In fact, we know always that limiting exists. So this is not a problem, but the problem is to show that this is always positive. And that's the problem. And so using this integration of measure, we can always assume that underlying system that is measure preserving transformation is there. So this is what we do when we start we use the part that this is there. And now we can observe that this expression here, so this is the scalar product of this function with this aberration operator, right? This aberration operator is precisely like in Hofstra-Ziegler theorem. In fact, so this Hofstra-Ziegler theorem for k equal 2, it was originally put by Forster. So he observed that this convergence can be established. But he gave a little bit different proof from this what I presented here. I followed more or less. I want to just show you that here we use the functional analysis sufficient to derive it. So therefore, but I believe that this is well known. Okay, so now and now we know here if we know that because this is now ergodic operator and we prove this Hofstra-Ziegler for k equal 2. Therefore, the limit exists here, so we can use dominated convergence theorem, for instance, and we know that the limit for this expression exists. So therefore, we even know that the limit exists, and we have to show that this is. And so, in order to prove the positivity, so we will use the fact, this decomposition of Jacobs Glitsberg will play an important role because it will allow us to reduce the problem to this multilinear form that corresponds to periodic functions. So in other words, because we know that this Jacobs Glitsberg splits our Hilbert space into the periodic functions and the weakly mixed. And here you see that. So for the Hofstra, we use the fact that the AP functions are eigenvectors of the complement operator. But here we use the fact that orthogonal complement of weakly mixing precisely AP function. So it's important here that L2 is split into HP plus W Hamilton. And okay, so this is what we do here. We split our characteristic function. So you see here we start with characteristic function, we split then into this projection pi of characteristic function of A. This is the projection on the AP function. And this is orthogonal component, which belongs here. And so we know, so one can show, so it's not difficult to show that, this projection preserves positivity. Okay, so one has to do a little bit of work, but one can show that the projection preserves positivity. We started with non-negative function or non-negativity. We started with non-negative function, we end up with non-negative function. This requires some argument, but it's not difficult to prove this. And or from general here, okay. And now by this decomposition of Jacobs Glitsberg, and the fact that our bilinear Hofstra-Ziegler converge to 0 for weakly mixing functions, we are reduced to showing that this limit is positive. Okay. So, and we also know that the integral of this measure of A, it's positive. This flows from this orthogonality, and because this is orthogonal to constant function. So we have this, and Yeah, and this is almost periodic function by the definition. And now if we take epsilon equal this, so from the proposition that we have already proved, we know that there exists integer j such that this set here is synthetic, which means that it has non-empty intersection with every interval of length j plus 1. Okay, so if we know this now we can see how this can be used to derive that the limit that we are interested in is positive. So we have this here. Okay. Now we can split this. So we know that. So here this is what we do. This is Jn. So okay, so we can bound this from below by restricting to the set for which we know that this integral has non-empty intersection with here each subset of length j plus 1. So therefore, if we use this definition, we know that we have this lower bound, which is of this form, and our epsilon is 1/2 times the cube of measure of A. So therefore, this now, and now this is here. I think that we should have half here, and okay, yes, that's the question. 1/2. But anyways, we end up with something which is positive. And so now by using the fact that, so here we use the fact that this, here we use Rutgers inequality, and this is what produces this this bound, and this is how we and this is and we are done. So therefore, here you see if we go back to this expression, now we proved that now we proved this that this limit is positive, and so we have to. And now, if we want to deduce Roth, we have to evolve correspondence principle. So we remember that the correspondence principle says that so we have subset E, subset of integers. Okay, and we assume that upper density is positive. Then there exists a measured preserving system X, B of X, measure, and certain measured preserving system here with the property, and there exists also there is a measurable set with the property that measure of A is equal to the density of E, and we know that this density is positive, so therefore the measure of set is positive. And also we know that in particular for every finite subset but of integers, but now we can have this particular choice, which will be which will be 0, presumably, and have this. Or maybe. That's what we did. And that's to. That. A. Intersection. Intersection. 1 is 2. And this is. This domain, this is the lower bound where you put the density of P. And here we have shift operator on the usual on the set of integers. And okay. And now, so this has positive measure. From this result, we know that this limit, so this limit inf is positive. Therefore, in particular, this implies that for infinitely many integers, the integrand and this guy here, here it's also super. We have this goes for infinity many, so therefore this is positive for infinity many integers. So therefore this is in particular an empty. We are done. So that's how we get. So if we apply this first inverse correspondence principle and we use this, then we can derive this combinatorial application. Okay, so I think that this is time to stop here. I'm not going to bother you with the details that we need because we don't have time. So if you are interested in, then let me know. I'll be happy to share with this slide that I used. They're all details. If you want to see how this works. All these technical things that we needed to that. But here I just wanted to emphasize that these Hilbert space methods are important here. Recurrence theorems are results in ergodic theory that in fact have this direct implications in combinatorics because of the Furstenberg correspondence principle. Which, as I said yesterday, it's a certain bridge between these two worlds. And so this is a nice thing, that we can use measure theory to interpret, combinatorial results in this measure theoretic framework. So that's I think that was an amazing idea. And deep inside Furstenberg, who observed that something like this is possible. And here you see that all these methods are very elegant, very soft. But the disadvantage of this, because we use, Berkhoff, we use von Neumann, these are statistical kind of results. So we can't say anything, quantitative. If you want to understand, this from the quantitative point of view, if you want to understand how many these arithmetic progressions, we can even count these arithmetic progressions. For instance, we will discuss everything on the set of, on the group Zn. Which is also, it makes sense to discuss, existential arithmetic progressions in groups Gn in the residual classes of modulo n. Then we can count them, and but for this purpose, for instance, in the case of Roth theorem, we have to use classical Fourier analysis, like Roth. If you want to do this in a more general setting, in this context of summary, longer arithmetic progressions, then we have to use higher order. So this is what we discussed in Van level. So I hope that I convey some ideas about So we have seen 3 different methods, 2 purely quantitative, and the third one this is qualitative. But in some cases ergodic theory proves some combinatorial results which are not available by using these methods from Fourier analysis or higher order Fourier analysis. So therefore, it's very, very powerful. And I think it's good to be aware, that we can use this kind of results to say something, in the natural world. So, and this, this area of ergodic theory is called these days, ergodic drums theory, where this combinatorial implications. Okay, so let me stop here. It's 12 or we could time.
Let's move on to Mariusz.
There's some theoretical discussion between Mariusz and the times.
Go on the right side, like this.
You can, but you have to consider some preliminary model, but this bound is very weak. So Derrida has a paper where he explains the context of Semerelli. It's a long paper. And this is what you get, it's very, very weak. But yes, you can. By using, this, there is a lot of in this paper now there is, machinery from Banach algebras. Things like this, so yeah.
What is the roughly of which size?
Okay, I can remember, but it's very.
Sorry, I couldn't hear. What did you ask?
So he asked if these ergodic methods can be quantified. If you get on the right hand side here instead of zero some lower bound, which is quantified. And I said yes, it's possible. But Terek has a paper, some paper, where he showed this, but this bound is very weak. But much better bound,
Useless.
if you use, for instance, much better bound you can get, if you use this higher order. So now this is the right to understand this, in the context of.
So when you say quantitative bounded, it means beyond positive density. Is that what you were asking?
No.
Like
So the behavior of this limit.
That it's bigger than something? Is that what? Oh, I see.
Yeah. So this is almost equivalent.
But I'm saying, yeah.
It's even worse than what you get from combinatorics, I think. Even worse than what you get from like the hypergraph regularity approach. It's also like power or Ackermann.
This is the alternative approach, right?
Yeah.
This hypergraphs.
Any other questions? So let's thank Mariusz again because we have.
Don't